In this video, we will discuss the central limit theorem, which is a key result that underlies most of the statistical inference you'll come across. You don't need to know it to get by practically in statistics, but appreciating it can be useful because it allows you to see the connection with much of the material that is of practical use, for example, confidence intervals and hypothesis tests. It also kind of unifies all of this material and helps you to see all of these tests and all of these estimation, etc., as part of the same theory rather than a collection of separate recipes. So to illustrate the central limit theorem, we'll talk about how it explains the sampling behaviour of a mean and also the sampling behaviour of a proportion. And this central limit theorem will naturally lead us to the normal distribution again. So we'll pull all that we've learnt on that together too. So we've already discussed the normal distribution, and you may wonder why it's so important. So there are two principal reasons. One is what you've already encountered, in that many distributions in the natural world just happen to be normal or approximately normal. So why might this be? Well, if you consider something like height, which can be seen as the sum of many small influences, genetic and environmental, and these influences act not only in a person's lifetime but also across generations, you can consider many of these factors as sort of independent random processes. Some will push height higher or taller, and some will push height lower or shorter, and the result is that many observations will fall around the middle and that fewer will fall further away, such that when the frequency of observations is plotted, the result is a nice symmetrical bell-shaped distribution. But the second reason why the normal distribution is important is concerned with statistical inference, and that's because it describes the sampling distribution of many point estimates when the sample size is large. And this result is called the central limit theorem, and is probably the most important result in statistics. Without it, almost all of what you learn in inferential statistics would not exist. So if we know that a point estimate follows a probability distribution, then we can use it to estimate uncertainty and hence do hypothesis tests and estimate confidence intervals. So let's first of all look at the distribution of sample means. This is useful as many of the statistics we look at involve a mean, for example the means in each exposure group or treatment group, etc. So say we have a variable that we know is normally distributed in a population. It has a population mean of 16, and we take 100,000 repeated independent random samples of size 25 to look at its sampling distribution. So here's the population distribution, and the graph here is an example of the distribution of a single sample of 25's observations, and the one at the bottom, this is what the sampling distribution would look like after 100,000 samples. It would be normally distributed, and you can see that with the overlaid normal curve, and it would also have a mean of 16 exactly on the true population value. So what if instead of samples of size 25 we took samples of size n equals 5, really small samples? Well, here's an example, and again the middle graph shows an example of the sample distribution from one solitary sample, and it resembles what you might expect from only such few observations. It tells you nothing. And here's the sampling distribution again at the bottom, and we can see that it's also normally distributed with the same value as a population parameter, the population mean. The only difference is, as you'd expect, the standard error or the sampling variation is much greater because it's a smaller sample. So what we've learnt is that if the distribution of the parent population is normal, then so too will be the sampling distribution, regardless of the sample size. But what if the distribution is skewed? So here's an example. We have a positively skewed parent population, and we've taken random samples of size 25 from it again. And there's an example of a random sample, and we end up with a normal sampling distribution for the sample mean at the bottom graph. So just because the source population is skewed, the distribution of the sample mean is normal. But what if we take smaller samples, say only size n equals 5 again, from the same skewed parent population? Well, in that case, we don't end up with a normal sampling distribution, but it's not too bad, it's almost kind of normal. But what if the population's even more skewed? So this is even more skewed than the graph you just saw. Again, here we're taking samples of size 25, but now the sampling distribution of the mean is less normal than for a less skewed population distribution. So the distribution of sample means from a skewed distribution is approximately normal, but it depends on sample size and the level of skewness. And what about a uniform distribution? Well, that's shown here. Again, let's take samples of size 25, and you can see what a sample would look like here in the middle plot. And importantly, the distribution of the sample means from a uniform distribution would be normally distributed and centered on its true value. Let's look at one last slightly unusual example. Here we have a bimodal distribution, which might occur, for instance, on a pain scale, people clustering at either end. Again, we take samples of size 25, and you can see an example sample here, and we end up with a fairly normally distributed sampling distribution of the sample mean. So fairly odd-looking population distributions may end up with a sample mean that follows a normal distribution over repeated samples. So we've seen that the distribution of the sample mean will be nearly normal even if the sample data are not quite normal. And there are some conditions attached to this. First of all, the sample size must be sufficiently large, or if not sufficiently large, the population that the sample was drawn from must have a normal distribution. And we also assume that the observations in the sample are independent, just as we described in the video on probability. So we'll now take a look at sampling distributions for proportions. So first consider an example. Let's say from a target population of 100,000 science students, we know that a meagre 10% of them like statistics. Suppose we take lots of independent random samples of size 10 and equals 10. We'd expect on average one person in each of those samples to like statistics. So our proportion would be 0.1. However, we won't get exactly one every time. So what we want to look at is the sampling distribution of samples of size 10, where the true population proportion, we call that pi, is equal to 0.1 or 10%. Let's also consider what the sampling distribution is for larger samples of size 20, 50 and 100, again with the same population proportion or population parameter of 0.1. Here's what it looks like using a sample of size 10. You can see that it has a mode of 0.1 or 1 out of 10, reflecting the true population value of 0.1, written as pi here. But it's fairly skewed. However, if we take samples of size 20, the shape of the sampling distribution becomes more normal. What if we take samples of size 50? Well, then the sampling distribution becomes even more normal. And with 100 observations, the sample is normal. So now we see that with large sample sizes, the sampling distribution of a proportion is approximately normal. And this is a central limit theorem acting again. Let's consider another scenario. This time we're interested in the sampling distribution of a proportion when the true population proportion is bigger, 0.25, so 25% instead of 0.1 or 10% that we've just been looking at. And you can see that with very small samples of only size 10, the distribution appears more normal compared with when we had a situation where our true population value was 0.1. And then with samples of size 20, it becomes even more normal. It's almost normal already. And with size 50, we can say that that sampling distribution appears normal. And 100, it just confirms what we've seen. So when the underlying proportion or true population proportion is bigger, we need fewer observations for the sampling distribution of the proportion to follow a normal distribution. So all of these figures I've described actually come from something called the binomial probability distribution. This distribution is a sampling distribution for the number or the proportion of binary events. So what we've just seen is that as the sample size increases, the binomial distribution approximates or becomes very close to the normal distribution. And this is also true for other probability distributions that we've not yet looked at, such as the exponential and Poisson distribution, and those are used to study rates. The conditions under which the sampling distribution of a proportion or the binomial distribution approximate the normal distribution are when n times the proportion is more than or equal to 10, and when n times 1 minus the proportion is more than or equal to 10. So if you stop and pause, this just reflects the fact that proportions closer to 0.5 require a smaller sample to approximate the normal distribution. And lastly, with all approximations, observations must be independent. Let's try to tie this together by talking a little bit about the normal distribution. So regardless of the shape of the underlying population distribution of a continuous variable, the distribution of sample means is approximately normal if the sample size is big enough. So for example, body mass index, which tends to be positively skewed in the population, has a sample mean that is normally distributed as long as the sample size is big enough. And we can calculate the standard error for a sample mean using this equation. It's the population standard deviation divided by the square root of the sample size. Now often we don't know the population standard deviation, so we estimate it using the sample standard deviation. And in some cases, when our sample is really small, we may not get a good estimate of this population standard deviation, and so we account for it, or we account for the uncertainty by using something called a t-distribution. More of that in another video. And we've also seen that the sample proportion will be normally distributed under certain conditions, in particular if the sample size is large. So here we've got the distribution of point estimates for the proportion of students that like statistics. It follows a normal distribution, just like the sample mean, except it's in different units. Its mean is 0.2, represented by the population proportion. And we can get an approximate estimate for the standard error of this sampling distribution using this equation. You don't need to remember these equations. Each type of point estimate has its own equation for the standard error, but the key thing to understand is that if we can assume that these point estimates are normally distributed, then all we need to describe the sampling distribution of the point estimates, or to describe the normal probability distribution associated with it, are its mean and its standard error. As said many times, the sampling distribution of the point estimates is a probability distribution, and you've seen how it's used for estimating confidence intervals and calculating p-values. This plot shows the standard normal probability distribution. It's called standard normal because we centered the population mean at 0 and transformed everything to units of standard errors, or Z units. And we can do this for any point estimate we like. So for example, the normal distribution of the sample mean of BMI, and our sampling distribution for the proportion of students who like statistics. And this is done by subtracting the population mean and dividing by the standard deviation of the sampling distribution, which is a standard error. So in these two examples here, we've assumed that our population mean is equal to the sample mean. The area under the curve captures the probability of observing ranges of values for Z, so the total area sums to 1, i.e. it has to take some value. To find these probabilities, we use statistical tables or a computer, because trying to solve the area yourself mathematically is fairly complex. Now we know some of these probabilities already from the 3 sigma rule. For example, there's only about a 5% probability of obtaining a sample mean more than 2 standard errors away from the true mean. However, this is approximate, The precise Z statistics, which would cut off the most extreme 5% of values, is actually plus or minus 1.96 Z scores. We'd write this as the probability of observing a Z statistic as extreme as 1.96 is 0.05. The two lines around the 1.96 just denote we mean bigger in terms of the absolute number of 1.96. We ignore the negative sign. We could also write this using the original scale of the variable. So for example, consider the sample mean and call it x bar. The probability of observing a sample mean more than 1.96 standard errors away from the population mean is equal to 0.05. We can use the normal distribution to work out probabilities of observing point estimates as extreme as what we saw for any type of population parameter we like, as long as it follows a normal distribution, which, as we say, can be a good approximation when the sample size is large. So you will see the normal distribution used to estimate confidence intervals and calculate p-values for other parameters, for example mean differences, risk ratios and regression coefficients. And all we need to use this normal approximation are the point estimate and some estimate of the standard error, and it's all because of this central limit theorem. So here are some facts about the normal distribution that are worth remembering. You may want to pause the video and digest some of this. And just to summarise, here's some key points from this video. Again, you may want to pause and digest some of this. Lastly, here's the new terms that have been introduced.